a typical indeterminate problem. Looks like this, where we have a beam supported by three cables. In this case, all the cables have the same length, and the beam is considered very rigid, and it has a load on it somewhere. And we need to figure out what the stress in the cable is, or what the tension is in the cables are. And this is an indeterminate problem because we have three vertical reactions, and we only have two equations of equilibrium that will work. We can sum forces in the y and some movements about some point. So let me read the equations that we have. Axial stress, P over A, and our deformation equation, PL over AE. So we have this beam, and if we do a free body diagram of it, has a load P on it, and then each of the cables is replaced with a reaction, and I'll just label them A, B, and C. And I can do equilibrium. We need to define the length of the beam somehow. And so let's go, this is equal to L. And then let's consider the location of P to be at some distance x from the left-hand end of the beam. And then the rest of the distance would be L minus x, where the supports are evenly placed with a total beam length of 2L, and the load somewhere on one side, a distance x from the end. So I'll do equations of equilibrium. Sum of forces in the x gives me nothing. So I'll sum forces in the y. Maybe I'll do that over here. Equal to 0. Say up is positive, and we get RA plus RB plus RC, all going up, positive, minus the load P is equal to 0, equals P. And we're going to set up a generic solution to this problem where certain things are known. And so we're going to know the length of the beam. We're going to know the location of the load, x. We're going to know the magnitude of the load. We're going to know the length of the cables. We have to figure out the deformations of the cables. But we're not going to be able to do that until we know that, until we know what the forces are in the cables and what these three reactions are. And we have three unknowns, P the unknown, and one equation, right? Three unknowns, one equation. We need two more equations. So we already talked about sum of forces in the x being useless on this problem, so we'll sum moments about A equal to 0. And let's go counterclockwise positive. And I'm summing moments here. RB is counterclockwise with the moment arm L. And RC is counterclockwise with the moment arm of 2L. L is L. And then we have minus P times a moment arm of X equals P times X. And so we can simplify this one to be RB divided by L everywhere plus 2 RC equals P times X over L, or PX over L. We have a second equation. right? RB, RC, two of our three unknowns. We have two unknowns, but now statics is exhausted. We've done everything we can with statics, and so we have an indeterminate, determinate, and we need a compatibility. Something about the deformations or rotations, displacement, something about how it deforms should give us another equation that can supplement our two statics equations and let us solve for different reactions. So let's look at the deformation. I'm pretty sure my assumption will be that if this is the original position and then I add the load, I think the whole thing is going to come down some, and then I think it's going to rotate some. And come across like that. Now, magnify or amplify, exaggerate, deformation. I think the move P is going to do that. And the cables were here. Like this. Original position. And so we see right here, we have a deformation of cable C. Right, so this is the length of the cables. This is the deformation of cable C, and this is the deformation here. Cable B. And this is the deformation here. Cable A. And so if the beam is rigid and doesn't bend or deform, or if it's at least an order of magnitude or more rigid than the cables that are supporting it, it's going to stay in a straight line. And we're going to see because of this cable's right in the middle. If this cable was offset, we would have to use similar triangles to make a little sophisticated analysis. But this amount right here, and this amount right here, we have this triangle. This triangle, and this is delta A minus delta C, right? Because delta C is up here. Delta C is up here. And this amount right here is delta B, total deformation of B, minus delta C. And this is length L, and this is length L. So if this wasn't centered, if this cable wasn't in the center, you'd have different volumes here. Similar triangles tells me that 2L delta A minus delta C is equal to this delta C. We solve that out, cross multiply, 2 dB minus C, cancel out the L's, equals L times delta minus delta C. Both of them are teams L, so now I'm going to cancel it out. And to the next step. 2 delta B minus 2 delta C equals A minus delta C. Or let's just look all over here. Make this side 0. So I can associate delta A. And let me bring the 2 delta B over, minus 2 delta B. And let me bring the delta C over, minus delta C already. And I'm going to add 2, so I'm going to have plus delta C. And that's our relationship between the three informations. When it's centered like this, it might be easier to realize that if I add this, let me go down. Add this amount to this amount and divide by 2, I'll get the average value, the value between those two, which will be this amount here. I'll just write that delta E plus delta C. And if I divide that by 2, I get delta B because it's right in the center. This is another way to come up with the same equation. Well, multiply both sides by 2, I get delta A. And now it's 2 delta B on the right. And it becomes minus 2 delta B. And then it's plus delta C equal to 0. You see, we get the same equation. Either of those approaches works. So I have my compatibility equation. I'm happy. Here it is, 0 is equal to, and just to fit all this in, I'm going to keep plugging it in. It's going to be PL over AE, okay, minus 2 PL over AE for B, and then plus PL over AE for C. Let's go back to our knowns. We're going to say that we know the areas. We know the material, we know the modulus of elasticity. And this L is our little, this is for each cable. This L is actually little L sub C, length of the cable. That's what I think that's bearing. And these are all equal. And so I can divide, I can divide each term by LC. And for a typical problem where E, they're all the same material. Now, if they're different materials, we got to factor in the ratios here, and the math will get a little more challenging. But if E is all the same, I'll multiply each term by E. So let's call this a constant. Call this a constant. And I'm going to multiply. That's an E, right? LC, right? And for the particular problem that we're trying to solve, setting up the generic equation, we're given the area of A equals the area of C equals 50 millimeters squared by the corner. And the area of B is equal to 30 millimeters squared. And so I'm going to set those, I'm going to call A equal to 50 millimeters squared, and then say the area of A equals the area of C equals area A, and the area of B is equal to 3/5 of A, right? 30 over 50. And so those I have to factor in. This results in 0. So I still have 0. And now P from A is the reaction of A, part A. LC over E cancels out. And I'm going to divide by the area of A, which we call just A, minus 2. This is reaction of B, divided by the area of B, which is 3/5 A, and then plus RC over A. And now we can multiply both sides by A and get rid of that. And let's simplify this question, this equation now. I'm juggling a few things in my head and time constraint to finish this right now. So RA is all by itself, and 2 divided by 0.6, it's going to be 10/3, I think. That's 10 RA plus RC. So I can multiply each term times 3/5. Know the form of the equation: 3/5 minus 2 RB plus 3/5 RC. And 2 again. Any of those are a good form. We have our third equation, equation 3. Use this one to go with equation 1 from statics, equation 2 from statics. So let's switch to a new sheet. We got 3 equations with 3 unknowns we need to solve for. Equation 1, RA plus RB plus RCP. Equation 2, no RA, RB plus 2RC equals P over L. And equation 3 is 3/5 RA plug minus 2RB plus 3/5 RC equals 0. I'm sorry, I think I'm going to rearrange this equation 3. I'm going to multiply it by a negative 5/3. Similar to before. But if I multiply this by negative 5/3, I get negative RA. Right, the 5's cancel out, the 3's cancel out, and I pick up the negative sign. I multiply this by negative 5/3, and I get plus 10/3, like that other equation, but the opposite sign. And if I multiply this by negative 5/3, 5's cancel out, 3's cancel out, I get minus RC. And if I multiply 0 by that, I still get 0, because now I'm going to add equations 1 and 3. And nicely, the RA's cancel out. RA minus RA 0, RB plus 10/3 RB, 3/3 plus 10/3, 13/3 RB, and RC plus negative RC is 0, and P plus 0 is 0. Sweet, we're happy because we have an equation that says RB is equal to 3P 13. Okay, does that make sense? Continue. We got to figure out the other two. Get RC from equation 2. Substitute here into equation 2. So we have 3P 13 RB is 2 RC equals PX over L. Subtract off 3P over 13 on both sides. And I'll divide by 2. So I'll get RC. Let me do the 2 here. I'll divide by 2. So we get 2L, and I get 26. Right. So I'm going to say RC is equal to, I'd like to pull the P out because it's a portion of P that's going to RC. And that portion should be X over 2L minus 326. Pulling the P out. Finally, I'll go to one of the equations to solve for RA. And I think I go to equation 1. This is RA. And let me say it's equal to P. And you see it. So we're going to subtract RB and RC off of P minus 3P 13 minus 3B. And that's going to be minus P X over 2L minus 326. And let's distribute this out again, same as we had right here. So that's X times B, 3P over 26. And then pull P's. I get 1 minus 3/13 minus X over 2L and minus 3 over 26. On the P out, and I have a function of X, number, number, number. It's the same thing as, let's make them 26, 26 minus, not 3/13, 6, 26 minus X 2L and minus 3/26. How many 26 do we have left? 26 minus 9, 17. Do that math quickly. 6, 17, 26. And it's positive. So P 17, 26 minus X over 2L. Use. And we can, yeah, it looks like got the complementary amount of P in your equation. And if now pull in some values, 15 kilonewtons, L 0.4 meters, X 0.2 meters. The values of E, where's the number sheet? Values of E, we don't need unless we're going to calculate an action information. We're just going to calculate the reaction. We do know it, but I don't know that we need it. Value of A, we've already said what those were, 30 and 50 millimeters squared. We need that if we're going to calculate a stress or a deformation, right? Maybe PL for I can pull this in for a second. We would need the A, calculate stress or deformation. We would need the E, calculate deformation. Length of the cables, L. This is the length of the cable, LC. If we wanted to calculate the actual deformations of the cables, then we would need LC. But all we need for this, these reactions are P, X, and L. I'm not going to bother pulling those numbers over. What else do we have here? It's P, LC, AE. Covered them all. Those are the only values we need. And calculator. Your B equals 3 over 13 times 15 kilonewtons. That'll give me 15 times 3 divided by 13, or 3.46 kilonewtons. And RC is going to be 15 times 0.2 meters over 2L, 0.8 meters. Meters over meter, it's just a portion of the 15 kilonewtons. It's a fraction, 1/4, minus 326. And so when we do that, 0.2 over 0.8 is 0.25, 1/4. And I'm going to subtract from that 3 divided by 26. And that leaves me the percentage of 15 that's going to RC, 2.02 kilonewtons. And RA equals 15, 1726 minus X over L, 0.2 to 2L, 0.8, 1/4. And so now I'm going to do 17 divided by 26 equals minus 1/4 that amount of 15. And we get 6.05. Something's wrong there. That is not the correct answer. 17 divided by 26 minus 0.25, 40%. And that's not right. There's some math wrong here. 5 minutes to figure this out. Substitute it in here. They didn't make a mistake. It's P minus RB. You made the mistake right there. Right? That's plus. Easy peasy. You probably noticed it watching the video. Kudos to you. Minus that, minus P times that became minus X over 2L plus 326. And Now it's 326. It became plus 326, and so it was 26 minus 6 is 20 plus 3 was 23. 26. So this should be 23. 26. Try it again. 23 divided by 26 minus a quarter times 15 kilonewtons, 9.52. Those are answers. So probably could have solved it numerically, maybe quicker. I think it would have taken about the same amount of time. Students don't really like working in variables, but uh, it is a much preferred method. It's easier, and then we have equations that are good for either applications. Um, so what I want to talk about is we we develop a an additional equation based on compatibility, based on some assumption of how it deforms. So want to see what would happen if I said P was equal to 15 kilonewtons, L was equal to 0.4 meters, and X was equal to 0. What do we get? Well, RB doesn't change because it's not a function of P. And then RC becomes a negative. Let's write it. RB equals 3.46. Stuff. RC becomes negative because it's 0 to 0 minus 326. So it's going to be 3 divided by 26 times P. I picked a 9 for a P. Divided by 9 times 15. So I get RC equals a negative 1.73 kilograms. And RA, this one should be easier. It's 2326 of P, right? 2326 of P. So 23, 26, 10 15, 27. Sure enough, if I add them up, minus 1.63, we get equal to P, equation 1, and we shouldn't check that. So 9, 10, 11, 12, 13, 14, 14 plus 0.5, 2 at 0.48, 1, 10 kilograms. But look, numerically, I can get answers, but they don't hold. Here's C. Now, if these were 3 rings, then RC goes down. But if X was equal to 0, then common sense would tell us that all the 15 kilonewtons goes right into this one, and these two might not support anything. Or since it's all attached, it has to rotate, and so our deformation doesn't look like this. Our assumption doesn't look like this. We always want to, that's, had we solved it only numerically, might get these answers and not be able to come back and look at it. The deformation for this one is going to look more like this here. And this just isn't feasible for this problem. So equations are not good in every case. And if we look at values, then we probably figure out, we have to set these equal to each other. We find out that x has got to be greater than L over 13, I think, for these equations to be valid. We have to check. Let me wrap this up. I'm late. Thank you very much.